Hello, let's resume shear analysis, okay? So first of all, let's take a look at the shear stress in the beam. Well, matter of fact, let's just take a look at the stress in the beam. So I have a beam, okay? Like so, and it's simply supported two ends. And this is neutral axis. And it's subjected to uniform distributed load like this. Okay, and you can tell that it's going to have bending and also shear force. So let's take a look at the stress that I can have on the beam. To show some generality, let's just pick three elements. Okay, and first I like to pick elements in the top part of the beam. Okay, another one in the middle part of the beam, and the third element at the bottom part of the beam. Okay, and I know in terms of stress state, I'll have a bending stress following the linear distribution. Right at the neutral axis, zero stress, and this is compression, this is tension, right? In combined stress state mechanics material, we talked about it, has a shear stress distribution, which is the maximum at the neutral axis and zero at two ends. So this is bending, this is shear. So the total stress state from these three elements, so stress on element 1, 2, 3, can be analyzed using these equations. So shear stress tau equal to VQ over IB, bending stress F equal to MY over I. And these element 1, is subjected to compression, since in the top, shear, okay, and then I will know that because it has combined stress state, my principal stress plane will rotate by the angle of alpha, and I have the total compression T2 and pure tension T1 along the principal plane. Okay, and also I know that the equation for principal stresses are that T1 O2 equal to half of F plus or minus square root of F squared divided by 4 plus tau squared. Okay, and also I know the angle tangent to alpha equal to 2 tau over F. Since alpha is small, so approximately equal to 2 alpha. Okay, so for element 1, this is the stress state. And I have compression going this way, tension going this way. All right, for element 2, since I don't have any compression tension stress since it's on neutral axis, I only have pure shear. And for those of you who are familiar with mechanics material, we talked about this. For pure shear stress state, the principal stress has a direction of 45 degrees, like so. Okay, and this is T2, compression, T1 tension. In element 3, instead of compression, I have tension because it is at the bottom half of the beam. Shear stress still going downwards. Okay, and now my compressive, my principal stress plane will go like this. My tension is going this way. My compression is going this way. And I'll have an angle of going the other direction by alpha. Okay, so summarizing all these stress states, I'm going to plot all these principal stress blocks on the positions of 1 to 3. So first of all, let's take a look at this one. So in red, I'm going to plot the orientation of the principal stress on top of the element 1. So I'm going to have a block just like that. Okay. And for 2, I'm going to have a block just like this. And 3, I have a reverse one just like that. And if I'm going to use dashed line to draw up the compression stress, okay, so the dashed line is going to go like this. Okay. Okay. If I'm going to use solid line, let's use different color, shall we? Solid, they say, and kind of purple line. This will be the solid line. Intention. Okay, so observing these dashed lines, I'm going to draw out all these principal stress directions on the beam. And when I draw them out, actually I will see this kind of distributions. Purple again, this is tension. Tension. Carefully see I'm connecting the element, tension. Tension. Okay. And tension. Okay. Sorry that the other side and the right hand side is not so symmetric, but it's supposed to be symmetric. Okay, with respect to the geometry. Okay, and now if I go back and draw the compressive stress in dash line red, it's anti-symmetric with respect to the purple one and goes like this. And again, it coincides with the purple line instead of the center line. Okay, so we call the solid line trajectory of tensile stress. And the red trajectory of compressive stress. Right? So now you can see if I have trajectory of tensile stress going this way, as in purple, okay? Imagine my crack is going to be what? My crack is going to follow the perpendicular plane. I'm going to use black. Follow the perpendicular plane. Of the purple line. So I'm going to draw these cracks. Okay, on the beam, like that. Okay, so now it's getting interesting because now I can take a look at these cracks. So I'm going to redraw it. Okay, I'm going to see the crack like this. Okay, I'm gonna have crack like this. And my rebar is gonna be here. Okay, and then I can say that these cracks on outside, and I call these a bending crack or flexure crack. Sorry. Let me take that back. When I see this vertical cracks in the middle, these are actually the flexure cracks. Okay. Now, why is that? Because you see they're on the bottom side. Has no shear or less shear. Okay, now correspondingly, these ones on the side, okay, called diagonal crack, mainly due to shear. Mainly due to shear. Okay, so now we can say that based on this. Tensile stress of various inclination and magnitude results from either going to be bending stress, vertical ones, shear, diagonal cracks, also in between bending and shear. Transitional cracks. Okay, so now what we're more interested right now is the diagonal crack. Which is due to shear alone. Okay, which means if you see these cracks here and here, these are the crack we need to take care of. Shear cracks. Okay? All right. All right. So now, if we do not take care of them, which means if no stirrups or web reinforcement provided, okay, what happens? What happens is that I'll have a analysis done in this way. That I can take the left end of the beam and I'll cut it across this diagonal crack to have a free body diagram like this. And then I know I have a reaction force here. I have a compression force from the concrete, I call it C1. I have a shear stress or shear force by concrete, and I call VCY. I have a diagonal shear contributed from the concrete through aggregate called VA. Then I have a compression force by the concrete from this side, C1 prime. Diagonal shear resistance from the aggregates, VA. And also I have rebar here. So through the rebar, Through the rebar, I have a tension force from the bar. I also have shear force resistance provided by the bar called VD. So I have a tension force here and VD here. Okay, and now, let's name some names, okay? So shear along diagonal cracks can be transferred through the following forces. Which are VCY, VCY is shear in the uncracked compressive zone. Also, I have VA, which is interface shear transfer. And normally this is from aggregate interlock. To put it more vividly, think about the crack, diagonal crack like this. I have some aggregates. Just breaking off, and biting on top of each other. On the shear surface. And this is called aggregate interlocking. And that provides the shear transfer along a diagonal crack. And also I have shear force from dowel reaction. So dowel action of the longitudinal reinforcement. Now this is the shear stress transfer diagram without stirrups, or web reinforcement. So basically I have concrete and I have longitudinal bar to provide a shear force. So now if I can say this, I'll say, now how about I call my total shear transferred in terms of VA, aggregate interaction, VCY, concrete, and dowel reaction, VD. And we call this total lumped together as VC, which means shear resistant provided by concrete alone. Okay, shear resistance provided by concrete alone. Okay, now there are several factors influencing BC. What are those? So first of all, of course, tensile strength of concrete, right? So the tensile strength of concrete, of course, will contribute to the shear resistance of concrete. Also, the longitudinal reinforcement ratio. Okay, and defined as AS, longitudinal reinforcement area divided by BWD. Notice that this BW for rectangular is this for T-beam, is this for I-beam, is this. Okay, quite different. But the D always depth of the bar. Okay. All right, so this is two factors. Now we also have to worry about the shear span and depth ratio. A over D. Okay, we'll talk about this later. Okay, and also we had to talk about the effect of lightweight and also aggregate. Okay, of course, since we have aggregate interlocking, we have to worry about maximum aggregate size. Okay, we also have to worry about the beam size, which is depth. And if there's any axial forces, which means if I have a beam here, do I have any compression? And I also have to worry about shear and moment ratio. Okay, so you can see it has a lot of factors to do with it. All right, so this is it today for the shear. Okay, we'll continue shear next Monday. All right.